So we'll talk about some analog and digital instruments, spectrum analyzers, antenna analyzers, oscilloscopes, and doing some RF measurements. Is everybody familiar with an oscilloscope? That's an oscilloscope.
You should rephrase that. That's a very nice locator. Not across the one.
But it's still an oscilloscope. It displays time domain waveforms.
It's like this illegal. It's
It's because mine broke. I had to buy a new one.
well, it's nice. With virus, it would break.
Huh?
So with virus, it would break. Oh, happening. So they say broken.
Well, you need one. Everybody needs one. Right now, it's looking at a signal on this little ARRL ATP modulation and fundamentals board that the ARL used to sell for basic radio type classes, but they stopped doing it. I don't know why. And I found it in a junk box at the Hamfest last year in Melbourne for $1. And it works, both of them. The other one's digital stuff. So if you want to play with it at the end, you can. Move the probe around and twiddle a knob. Most of the oscilloscopes today are digital. There's a couple issues where we talked about aliasing. You can have an aliasing problem if you're have the sweep, the horizontal sweep too low, which means you're not sampling at twice the frequency you're trying to look at. So you will get some what appears to be some lower frequency signal than you're actually measuring. The limit on a digital oscilloscope is like when we talk about SDR radios, because they use an analog to digital converter. So it's the sample rate of that A to D converter which determines the highest frequencies that you can see, because you have to sample at least twice, whatever that frequency is. And then the number of bits is going to give you the dynamic range. In other words, from the maximum it can read down to the minimum it can read is determined by the number of sample bits. So which of the following limits the highest frequency signal that can be accurately displayed on a digital oscilloscope? Or did you look the answer up? Did you look the answer up? Okay. The sample rate. And like I said, with the aliasing, if you have the horizontal sample rate or time base too slow, you're not going to get enough samples, so you get the aliasing issue. What is the effect of aliasing on a digital oscilloscope when displaying a waveform?
Alpha?
Alpha. Whether it's an analog or a digital oscilloscope, it has what's called a trigger function, which determines when it tries to sample the input signal so that you can have a stable signal representation. If it's not triggered where it can synchronize it, you'll just see a moving waveform. So you have to use the triggering mode, and there's as many as 4 or 5, maybe 6 different modes on a lot of them that you can select. AC coupled, DC coupled, a level, a ramp up and down. And most of them usually have what's called line, where it syncs on the 60 hertz line signal, because they're normally plugged into AC. And it uses that particular point to sync things. So in their example here, if you were looking at a linear power supply, if it's going to have any ripple in the output, it's probably 60 cycle or 120 cycle ripple, because it's generated from an AC signal, 60 cycle signal. So in this case, line trigger mode would allow you to sync up on that because it's going to be at the same frequency. It's a long way to go for one question. Which trigger mode is most effective when using an oscilloscope to measure a linear power supply's output ripple? Delta. When you're trying to make measurements, particularly at the higher frequencies, you need to keep the, usually these have a ground lead, and then so you have your 2 connections. You want to be able to keep this as short as possible. And for higher, really high frequencies, they make different tips for these where it's very, very short. And in fact, some cases it's like 2 pins where you can reduce it down, because at the higher the frequency, that becomes a fraction of the wavelength. So it does affect the measurement. And it also, the longer it is, will pick up stray noise on that little loop. Which of the following is good practice when using an oscilloscope probe? Minimize the probe ground length. They say good quality passive oscilloscope probes. I guess there's some cheap ones that don't have that adjustment, but I've never had one. Most of them you have the ability with a little adjustable capacitor that's in the, usually the base of the probe or somewhere on it, that you can adjust to adjust out stray capacitance. And you usually do that by they will have a special probe if you don't have it grounded. And you'll generate a square wave, and you adjust the probe to make a perfect, you'll try to get a perfectly square flat top on the square wave. Some of the things you may see is something like this, or like the top or the middle, whichever way it is, and you adjust it out to try to get this, because they typically generate a very good, sharp square wave with high rise times. How is compensation of an oscilloscope probe performed?
Shell.
Alpha. Okay, next is a spectrum analyzer.
Stop it. What is this? Like, why do I need this?
Because it's on the exam.
Okay.
If you don't ever intend to build anything or repair anything, you don't.
Okay.
But it's a possible test question.
I guess, Bob,
Yeah.
would you mind explaining a couple of practical applications, specific practical applications for an oscilloscope?
Well, if you're designing or troubleshooting a piece of equipment, you can use it to go probe around and look at different points in the circuit to look at the waveforms to see if they're uh, what you expect. And you can
How
do
would you
measurements.
how would
You
you
can
know how would you know what it should look like, what it should look like?
Well, if you don't, then you don't need to go probing around. So you have to have some foreknowledge of what it is you're going to go look for. Like in the case, if you're checking to see if your oscillator is oscillating, you're going to expect to see hopefully a nice sine wave output from it. You can make amplitude measurements with the oscilloscope. It'll tell you the peak values. You can make time measurements or wavelength on what the frequency of the signal is. See if frequency is changing. You can see distortions in the wave. If it's not a pure sine wave, it means you've got some other frequency components in there to make it all funky looking.
Okay, thank you.
You have to keep in mind, normally commercial equipment or technicians, they just sell you or provide you with a service manual. And the service manual will give you.
Usually, they'll show you at this point, you're supposed to see this.
Expect to see it. I need to service way.
There's a lot of that going on.
Yeah, I don't know.
But what the oscilloscope does is show you time domain. So it shows you the amplitude of a signal versus time. We talk about a spectrum analyzer, it shows you the amplitude of the signal with respect to frequency. So the horizontal axis will be a frequency range. And in the case of, if I looked at a square wave with the spectrum analyzer, I'm going to see a little amplitude spike for every odd harmonic of that fundamental frequency, which is how you make a square wave. So you see this little series of peaks at odd harmonic frequencies displayed. If you look at that same signal with the oscilloscope, you're going to see a square wave like that. So they do one's time domain, one's frequency domain. And in both cases, they're showing you amplitude versus one of those. You normally would use the spectrum analyzer if you're checking for spurious outputs or harmonic, third harmonic distortion type outputs. The regulations on transmitters, if I remember right, the third harmonic has to be what now 42 dB down or something like that. So that's one of the things you would check with the spectrum analyzer. This is just kind of a comparison. You know, you see this nice sine wave. uh, if you looked at it on the oscilloscope, but if it had any modulation in it, what you're going to see on the spectrum analyzer is that carrier in these little sidebands. Which of the following parameters does a spectrum analyzer display on the vertical and horizontal axes? Which of the following test instruments is used to display spurious signals and/or intermodulation distortion products generated by a single sideband transmitter? Next, we have an antenna analyzer. I don't have one. But I did bring, let me talk about spectrum analyzer. This is called a tiny spectrum analyzer. It's tiny, but it works. And this can be used as an antenna analyzer. It's called a nano VNA, but it's more of a vector network analyzer. Antenna analyzers are typically made to check SWR. They may do a few other functions, but basically you're looking at the signal standing wave ratio and trying to tune your antenna for the lowest SWR, and it'll show. It may do a graph depending on the model and show you the SWR over a frequency range, so you can see multiple bands. Let's see what else. They'll tell you what the impedance is. Sometimes they'll display it in the normal Z equals R plus or minus JX form. So you can see what the real resistance is and what the reactance is. I think maybe some of them can do a time domain reflectometer mode, not all. You get what you pay for. And this is a picture of one of the, not sure which one that is. It's one of the nano VNAs. There's several variations of it. It's like most things, the people that first came out with it, then it got copied. So there's a bunch of different versions that aren't necessarily compatible between one another. Which of the following is used to measure SWR? We finally got a delta. Because we talked about directional watt meters before. You measure SWR with the ratio of the forward and reflected power, remember? Which of the following is an advantage of using an antenna analyzer compared to an SWR bridge? And the SWR bridge measures forward and reflect. Yeah, unfortunately, the analyzer doesn't tune your antenna.
Okay.
So D is definitely out and A is out.
PCARS actually has one antenna analyzer you can borrow. So CMFJ one, I guess the Bravo version of it, but I've used it before. And it's analog. It's analog.
Yeah. Which of the following can be measured with an antenna analyzer? What are the odds of it being D?
Say the.
I'm not exactly sure how you measure velocity factor unless you know the physical length of the cable. It'll give you the time delay.
I think you have to factor that in when you have to put in a parameter or something like that, and at least in an NFJ one, and it gives you a velocity factor. And didn't bring the expert I have gives it to you.
And you have to tell it the length.
Confidence. I think it's like a king, they compare to painter.
Right.
So.
But that just gives you time delay.
Yeah, like I've got the same when you have. Working with like.
I'll have to check. Okay, another piece of equipment is a frequency counter, which sometimes you can use to measure frequency. So if you want to see if you're transmitting on the right frequency, you might want to check the actual output or your internal VFO oscillator and actually measure the frequency that is set for. And it may be different than what you're seeing displayed. There's possibly some error there. Normally they'll have a fixed range, and if you need to measure a frequency that's higher than the frequency counter, you have to add what's called a prescaler, where it actually divides the frequency down and presents a lower frequency to the frequency counter. A lot of times they'll have, yes?
You might cover this in the next slide, but let me ask it anyway. What's the difference between a frequency counter that can measure, or maybe there isn't any difference between a frequency counter that can measure a regular analog signal and one that can measure a digital signal like, say, DMR?
Well, a frequency counter is going to have a hard time doing a measurement on a complex waveform. Normally, you would use it on something that's sinusoidal or a digital square wave type signal. If you've got a complex waveform, I'm not sure what kind of reading you're going to see. I wouldn't trust it. For something like that, you need to use an oscilloscope or look at the spectrum analyzer to see what the components are.
Okay, thank you.
I was going to say some of the frequency counters have prescalers, some built into them, and you go different ranges, and they can divide down to get it to the basic frequency counter. There's just a typical picture of a cheap one you can buy. I'm sure it's made in China. What is the purpose of using a prescaler with a frequency counter? Help it.